Hello, good morning. Welcome back to our last class in the bridging program for further math. So, today we're going to wrap up the rest of the chapter. There's actually one little part that we're not going to cover, that would be matrices. Hello, morning. Because, if I'm not mistaken, matrices have been removed from AdMath, which means you guys know absolutely nothing about matrices. So, if we want to go into that part of the chapter, we're going to have to talk about matrices, and that is another whole new can of worms, which I don't think we have the time to open in one class. So we're going to skip that part of the chapter. And if you do further math, at some point we will go through matrices together. Anyway, so today we're gonna do I'm gonna show you how to do divisibility type questions and inequality type induction questions. So let's get to it. Also, if you guys have anything you want to ask from the previous exercise, feel free to let me know, and I'll go through those as well. Okay, so okay, you know what? Let me just use this. Yeah. Let's say we have some function fn is equals to 2 to the power of 2n plus 5, where n is equals to, where n is a natural number, that means positive integer, and it includes 0. So this symbol here means including 0. This means this is a positive integers. Okay, and we need to show that this function is always divisible by 3. So show by induction that it is divisible by 3. Okay. So there are two ways to interpret divisibility. One is something that you probably already know. If it is divisible by 3, that means when you divide it by 3, you get no remainder. All right. And the other thing is that function has to be a multiple of 3. Okay. So another way of writing this is, oh, actually, you know what? Let me just rewind a little. So we need to show that it is by induction divisible by 3. So how do we do that? We're going to use the same steps that we've done for the previous questions. We're going to start by proving the base case. So we're going to do H0. So when n is equals to 0. So normally for the questions that I've shown you, n always starts at 1, correct? But for this particular case, n would start with 0. And the reason we start with 0 is because the smallest case here is when n is 0, because n includes 0. Okay? So when n is equal to 0, what do we get? We get 2 to the power of 0 plus 5. 2 to the power of 5 is, what was it? Is it 32? 32, I think. Wait a minute, 32 is not divisible by 3. Hang on. Did I write the wrong question? Let's check real quick. Oh, I did. I did mess up. Hang on. I messed up. this should actually be 2n plus 2 plus 5. There we go. All right. So this is actually 2 to the power of 2 plus 5, which is 9. And we can write 9 as 3 times 3. So it is divisible by 3 because it is a multiple of 3. Okay? So therefore, H naught is valid. There we go. Okay, so the trick when it comes to doing these questions is by showing that the difference between fk plus 1 minus fk is also a multiple of 3. So we need to show something like this. Why do we have to do it like this? Well, let me try to explain it this way. Let's say fk, so let's say fk is divisible by 3. So fk is equals to 3k, where k is some integer. All right, but the point is it is divisible by 3. Okay, and let's say we have fk plus 1. Or let's say you know what? Let's put another function. Let's say gk. Or let's say we call it gl, whatever. So this is 3l, where l is another integer. So the point here is we have two different functions and they are both multiples of 3, which means they are both divisible by 3. So if we take one function and we subtract that with another function, and they are both divisible by 3, the difference in the functions, oh wait, I messed up. This is 3l minus 3k. The difference in the functions is going to be divisible by 3 as well, because it's also going to be a multiple of 3, because you can always factorize the 3 out. Okay, so if both of these are divisible by 3, then this should also be divisible by 3. Similarly, if this is divisible by 3 and this is divisible by 3, this should also be divisible by 3. Okay, so if two of them, so if let's say we have 3 terms here, 1, 2, and 3, if 2 of these 3 terms are divisible by 3, then the third term is going to be divisible by 3 as well. Okay, so that's the whole argument that we're trying to go for here. Okay, so let's do hk. So when n is equals to k. So we're going to say when n is equals to k, fk is equals to 2k plus 2 plus 5. And we are going to assume that this is in fact equals to 3l, where l is some integer. So basically we're assuming that this is divisible by 3. So we're going to assume this is true. Assume this is true. Okay, let me just get rid of this. Right. And then for the inductive step, hk plus 1. So we need to show that fk plus 1 is in fact equals to 3m, where m is some integer. Okay, so how do we do that? Okay, so this is, I'm just going to bracket this because this is our objective. We haven't actually shown it yet, but we are trying to show it. So in order to show this part here, we need to take the difference. Oh, whoops, I forgot to change the color. Hang on. We need to show that the difference between fk plus 1 and fk is going to be some multiple of 3. right? So fk plus 1 is going to be 2 bracket k plus 1 plus 2 plus 5. And then fk is 2k plus 2, and then minus 5. So these two would cancel. And what do we get? We get 2k plus 4 minus 2k plus 2. And then we can say fk plus 1, and I'm going to move the fk over here. All right. Okay, what else can we do? Let's see. Well, what we can do here, we can write this as 2. Let me just take out the 2 here, so k plus 2. Oh wait, no. Wait a minute. Let's check something, see if I messed up. Yep, that seems right. Okay. Okay, yep. So far so good. So what we're gonna do next is we need to split up the powers. So you get something like this using the rules of indices, right? So you're gonna get this times this plus fk. Yeah, actually, you know what? I'm just gonna leave the left side untouched for now, so it's less confusing. So this guy is gonna give me 16 times 2 to the power of 2k minus 4 times 2 to the power of 2k. So if you have 16 of something minus 4 of something, we get 12 of something. Okay. And you can see that this guy, we can actually take out a 3, and this becomes 4 times 2 to the power of 2k. There we go. So this tells us that the difference between the two functions is also a multiple of 3, because 2 to the power of 2k is just some integer, and if we take the integer and multiply it by 4, we just get another integer. So this has to be a multiple of 3. So if the difference of two functions is a multiple of 3, and assuming that, fk is in fact a multiple of 3, so it's, divisible by 3. So if these and this are both divisible by 3, that means this has to be divisible by 3 as well. If this doesn't quite make sense to you, let me just rewrite it in this form. Then maybe it might look a bit more sensible. There. So if you have something that is divisible by 3, okay, you know what? Let me just do it like this. And then we're assuming that fk is divisible by 3, so we can write this as 3l. So we can take 3 out, which means we get 4 times 2 to the power of 2k plus l. The dot here that I've used is actually another way of writing times, by the way. So typically in A levels, it's best to use a dot rather than a times, because when you are dealing with vectors, or vectors, when you're dealing with vectors, there are two ways of multiplying vectors. There's the cross product, which is typically denoted by the notation that you are familiar with, and there's also the dot product, which is, a dot. So typically we use a dot because it is less confusing. It is also less similar to the unknown x, which sometimes people use. So if you use x and times and they both look like a cross, it can be a bit confusing. So anyway, this is actually 2k plus 2 plus l. There we go. So that's how you show that fk plus 1 is in fact divisible by 3. So finally, you can say, hang on, let me just go back a bit. So having shown that fk plus 1 is divisible by 3, we can actually say that hk is going to give us hk plus 1. So basically this statement tells us that if hk is true, then hk plus 1 is also true, as we have just shown right here. Okay, but this is assuming that hk is true. But now we're going to combine this guy and our base case to show that it is true for any n greater than or equals to 0. So since h1 is true, then using hk to hk plus 1, h2 is also true. Therefore, fn equals to 2 to n plus 2 plus 5 is true for all n greater than or equals to 0. This symbol means for all. Okay, so that's how you prove this by induction. So if h1 is true, that means using this, h2 must be true as well. And then using this again, h3 must be true, and so on and so forth until infinity. So that's how you prove that it is true for all values of n. Okay, that's it. Right, let's do one more example. Let me just move this. Hang on, let me just say this is example 1. Let's move this down here. Let's do example 2. So we're gonna do fn equals to 3n plus 2 plus 5. And n is a natural number including 0. Yep. Okay, so we have to show that it is divisible by 2. Okay, so let me just move this aside. So prove that two modulus this using induction. Okay, so this is just mathematical jargon for this function is divisible by this. And the way you pronounce this, I suppose, is you say 2 mod and then the function. Okay, so basically this just means show that, prove that this is divisible by this, and you have to use induction. Okay, so how do we go about doing this? First, you start by proving the base case again. So when n is equals to 0, what do we get? Well, we get 3 to the power of 2 plus 5, which is 14. And as you can see, this is 2 times 7. Therefore, we have proven the base case. Hey! And then we're going to say that hk is now n is equals to k. So fk is equals to 3 to the power of k plus 2 plus 5. And we're going to assume that this is in fact equals to 2l, where l is, you know, some positive integer. We're going to assume it is true. Okay. Next up, we're going to do k plus 1. And in order to show that fk plus 1 is divisible by 2, so let's say this is, you know, we're going to have to show that this is equals to 2 times m, where m is some positive integer. And this is our goal. We haven't proven it yet, but this is what we are trying to get to. So we need to do fk plus 1 minus fk. Okay, what do we have? We have 3k plus 1 bracket plus 2 plus 5 minus fk is 3k plus 2 plus 5. Okay, there we go. So the 5s and the 5 would cancel, and then simplifying this shenanigans, we get this guy minus this guy. And then we're going to split out the powers. So we have 3 to the power 3 here, and 3 to the power 2 here. So essentially we have 9 times 3 to the power of k minus, oh sorry, not 9, it's 27. 27, and then this one is 9 times 3 to the power of k. So 27 minus 9 is 18. Okay, and then now we're going to move the fk over to this side. And assuming that fk is divisible by 2, we are going to have 2 times L here, which means we can factorize the 2 out, and then we have 9 times 3k plus L. So this is actually, you know, all of this is just some integer, so we can actually write it as 2m. So shown. Ta-da! Okay. So now we have to write our conclusion here. So therefore, Fn equals to 3n plus 2. Hang on, let me just write it here. Therefore, by induction, this function is divisible by 2, or you could say, instead of writing this, you could say by induction 2 mod this guy for all n that is a natural number including 0. There, so that is a very concise form of the inductive conclusion. Ta-da! And done. Okay, there we go. This is example number 2. Let me just move this guy here a bit. Example 2. Right. Let's do example 3, shall we? Hopefully you guys are getting the hang of this. Does this make sense? Is this all right so far? Is there anything you guys want to clarify or ask? If there is, feel free to let me know. Where's my phone? Yeah, I'll just leave it here. You can just message me directly if you want. Okay, let's go over here. Let's do example number 3. Okay. So this also works for polynomials. So let's say we'll just do an example involving a polynomial. Get rid of that. So show, oh, hang on. Prove by induction. Prove by induction that this function here, n squared plus n plus 2 squared, is divisible by 2. Okay, right. So let's start with the base case. Oh wait, I haven't defined the domain for n yet. So n is going to be a natural number including 0. Okay, there we go. So base case n is equals to 0. F0 is equals to 0 squared plus 0 plus 2 squared, which is going to give us 4, which is 2 times 2. Therefore, the base case is proven. Okay, and then for the k case, we're going to get n equals to k. Therefore, fk must be equals to k squared plus k plus 2 squared. And we're going to assume that this is in fact equals to 2L, where L is some integer. Assume it is true. You don't really have to write this, but I'm just writing it for clarity's sake. Anyway, let's do k plus 1. K plus 1 is going to be fk plus 1 minus fk. All right, what do we get? Well, you know what? Let me just write down the goal first, because that's what we've been doing so far. You don't really have to write down the goal, by the way, in the exam. I'm just writing it because it makes the most sense, seeing it like this. So fk plus 1 is equals to 2m, where m is some integer. So this is what we are trying to get to. Okay. So to do that, we have to write fk plus 1 minus fk, and work out what the differences. So the first one is going to give me k plus 1 squared plus k plus 1 plus 2 is k plus 3 squared. And then I'm going to subtract that with k squared, subtract that with k plus 2 squared. Okay. And this is going to take a while to expand and simplify, but yeah, let's go ahead and do that. So we have k squared plus 2k plus 1 plus k squared plus 6k plus 9 minus k squared minus k squared. This one is going to be minus 4k. And then last one is minus 4. All right, so we're going to get rid of the k squared here. What else can we get rid of? We can get rid of another k squared. There we go. And then we have 2k plus 6k, 8k minus 4k is 4k. Then we have a 1, 10, and then 6. All right, and then we're going to move the fk over. And what is fk going to be? Well, fk is actually 2m, 2l. Okay, we're assuming that to be true. And now we can factorize 2 out from the entire thing, which gives us 2k plus 3 plus l. And as you can see, this is merely another integer, so we can write this as 2m. And therefore, we have shown that this is divisible by 2. Hey! Okay, so therefore, by induction, this function n squared plus n plus 2 squared is in fact divisible by 2 for all values of n, such that n is a natural number, including 0. Ta-da! Done. Okay. Let's do one last example involving divisibility. I mean, it's the same thing, but okay, fine. Let's do one more. Let's do one more. All right, let's do one more. This is another polynomial example. So example number 4. Proof. Proof by induction that f n equals to, what am I doing? Divisible by 3. Okay, so proof by induction that this function here is divisible by 3. N plus 2 cubed plus 2n plus 1 cubed, such that n is a natural number, including 0. Okay, so if you're feeling adventurous, you can try this alongside me and see whether you can get the same answer. Okay? All right, here we go. Our base case is going to be when n is 0. So that's going to give me 0 plus 2 cubed plus 2 times 0 plus 1 cubed. And that's going to give me 2 cubed, which is 8. And that guy here is going to give me 1 cubed, which is 1. So we got 9. 9 is actually 3 times 3. So we have shown that it is in fact divisible by 3. Yeah, so H naught is true. Cool. Then we're going to do HK. HK is when n is equals to k. So FK is going to be equals to k plus 2 cubed plus 2k plus 1 cubed. And we're going to assume that this is in fact equals to 3L, where L is some positive. Oh, well, it doesn't have to be positive. L is some integer. So we're going to assume it is true. Okay, so HK plus 1. This is when n is k plus 1. And our objective here is to get fk plus 1 is equals to 3m. M is some other integer. So this is our objective. Always good to know what you're trying to get to. And the way we go about doing that is by taking the difference, like what we have been doing the last 3 examples. So fk plus 1 is gonna be, where is fk plus 1? K plus 3 cubed plus 2k plus 1 cubed, and then minus that with k plus 2 cubed, minus that with 2k plus 1 cubed. Okay, so this is gonna take a while to expand, but we can just use the binomial theorem. Technically, you don't have to use the binomial theorem if you remember the triangle, you know, the binomial theorem triangle. So you can remember what the coefficients are. In this case, it's going to be 1, 3, 3, 1, right? Pascal's triangle. So that's going to give me k cubed plus 3k squared plus 3k. Oh, wait, hang on a second. This one is going to be 3 times 3, so it's 3 times 3, so this should be 9 actually. This should be 9k squared. Then this one should be, wait a minute, let me think. Oh, whoa. This should be 3 times 3, so it's 9. This one should be 3 times 3 times 3, which is 27k. Then this one should be 27. Is that right? So we know the coefficients are 1, 3, 3, 1. And this one should be 3, 0. This one should be 3, 1, 3, 2, 3, 3. So 3 times 3 is 9. 3 times 3 is 27. Yeah, okay. This is correct. Yep, okay. This should be correct. Okay, move that away. So next one we have, so you simplify this guy, we get 2k plus 3 cubed. So the first one is going to be 8k cubed. The second one is going to have a coefficient of 3. So it's 3 times 2k squared times 3 to the power of 1. Then we have 3 times 2k 1 times 3 to the power squared. And then plus 3 times 2k 0, 3 to the power 3. Okay, then lastly, this third term here, k plus 1 squared cubed, is going to give us k cubed minus, what's this? Let me think. K squared, so 3k squared times 2 is 6k squared. And then 4k times 3, it should be 12k. Should be 12k. And then this one should be minus 8. There we go. Then after that we have this guy here. So that's going to give me 8k cubed minus 3 times 2k squared times 1. And then minus 3 times 2k to the power 1 times 1 squared. Then minus 3. There's no 3 here. Minus 1. There we go. So I've been using the binomial theorem to expand this, okay? Right, so let's simplify this monstrosity. What do we get? This guy here, plus 27, plus 8k cubed. Okay, you know what? I'm just gonna write it like this. So 8k cubed here. Next one is 9 times 2 is 18, so plus 18k squared. Next one is going to be 9 times 3, 27, 54. 54k. Then we have 27 times 3. 27 times 3 is 81. And then we have minus, this is plus, and then we have minus k cubed, minus 6k squared, minus 12k, minus 8. And then we have minus 8k cubed. This guy is minus 12k squared. And the last one here, this guy is 6 times 1, so minus 6k minus 1. Then we're gonna just add it vertically. We get 9, 8. Oh, they just cancel each other out. Cancel, 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 gone. Then this guy we have 27 minus 28. No, sorry, 27 minus 18, which is 9. 9k squared. And then we have 81. 81 minus 18. 81 minus 18. What do we get? We got 63. Oh, 63k. Okay, 63k. And then we have 27 minus 27 plus 81 minus 9 is 99. Oh my god, that took forever. Okay. So finally, we're going to move the fk over here. So that's going to be plus fk. And as we know, fk is in fact 3l, right? Because we assume that to be true. So now we can factorize 3 out from this entire thing, which is going to give us 3k squared plus 21k plus 33 plus l. And as you can see, this whole thing is just some integer, which we'll call m. So therefore, this is equals to 3m. Oh, done. We have finally shown that it is in fact divisible by 3. So therefore, by induction, this function here is divisible by 3 for all values of n such that they are natural numbers including 0. And done. Okay. There we go. We're finally done. So next, I'm going to show you how to do induction for things involving inequalities. Okay, you guys ready? 5, 4, 3, 2, 1. Here we go. So let's see. What's the example that I was going to show you? Let me think. Yeah, I think I remember. Okay, so we're going to move this over here. Example number 5. So, prove by induction that the value 2 to the power of n is always greater than n. For n is some natural number, for, a natural number n. Okay, so how do you do this? Well, first we're going to say, we're going to do the base case as usual. We're going to say n is equals to 1. So when n is equals to 1, the left-hand side is going to be 2 to the power of 1, which is 2. And the right-hand side is, well, 1. Okay? So is 2 greater than 1? Yes, 2 is greater than 1. So therefore, the base case is true. Oh, okay. And let me just show you something real quick. What if we do 2 to the power of 2? 2 to the power of 2 is going to be 4, right? And 4 is going to be greater than 2. So the h1 is also true in this case when n is equals to 2. So you can see that, I mean, logically, if you think about it, 2 to the power of n is always going to be greater than n, right? But that is not enough for a mathematical proof. We can't just say, oh, logically it should be true and therefore it should be true. No, we have to show it by induction. So let's do hk. Hk is going to be 2 to the power of k is greater than k. So we're going to assume this is true. Assume this is true. Okay? And then we have to show that hk plus 1, 2k plus 1 is greater than k plus 1. So this is our objective. This is what we are trying to show. This is our goal. So how do we show this? Well, we're going to start with the statement that we know is true, which is, spoiler, this guy. Hey. So we're going to start with this. So assuming we have 2k greater than k, we know this is true because we're assuming it's true. And we're going to multiply both sides by 2. So we're going to get 2k plus 1 greater than 2k. Okay? So we get this guy here. Now, if we look at this guy and we look at our goal, you see that the left-hand side is actually the same. Huh. So we know that this thing is true, and this is our objective, right? So if we look at this guy on the right here, 2k versus k plus 1. So if k is greater than 1, then 2k must be greater than k plus 1. Wouldn't you agree? For example, if I put k is 2, then I would have 2 times 2 greater than 2 plus 1. So 4 is greater than 3, right? In other words, I can rearrange this. So I'll just put this k is greater than 1. Yeah, if I rearrange it, hang on, how should I write this? If k is greater than 1, then if I multiply both sides by 2, I'll get 2k is greater than 2, right? And I can move one of these, how should I even explain this? Hang on, let me think. Okay, if I add k on both sides, you see that I get 2k greater than k plus 1, which is the statement that we get. You can see that this guy must be greater than this. Okay, so since 2k is greater than k plus 1, therefore this guy must be true, because this guy, we know that this guy is going to be greater than 2k. Therefore, this guy must be greater than something that is smaller than 2k. If that does that make sense to you? It's like saying some function that we have, fk, is greater than 10. Therefore, fk must also be greater than... Wait, How do I even explain this? Let me think. Oh, wait, I think there might be a mistake in the question. Because now that I think about it, it doesn't seem to make sense. Because if I say fk is greater than 10, right? Which is basically this part here. Does that mean fk is greater than 9? Because 9 is smaller than 10, since 9 is kind of like this part here? No, right? Just because fk is greater than 10. Oh wait, what am I thinking? If fk is greater than 10, then fk must also be greater than 9. Okay, never mind. I was just just pretend I didn't say anything for the last 10 seconds. Okay, so fk is greater than 10. So we've proven this, right? So we've shown this. We've shown this. This is actually this blue statement here, because we know that 2k is greater than k plus 1, right? So we've shown that fk is greater than 10, which means fk must be greater than 9 as well. Obviously, right? If something is bigger than 10, it also has to be bigger than 9. Therefore, it has to be, this statement here has been shown to be true as well. Does this make sense to you guys? Yes? I hope so. Right, so since 2k is greater than k plus 1, therefore 2k plus 1 must be greater than k plus 1. That means we have shown our goal. Therefore, hk to hk plus 1 has been proven. So if h0 is true, then h1 must also be true. Therefore, by induction, 2n is greater than n for all n that belongs to the natural number set, for all n that is a natural number. And that's how you deal with induction when you have an inequality. Yeah, there we go. Okay, I'll do one more example, right? One more example. So I think I have a question here. I think it's this one. I think it's this one here. Question 8. 4n greater than 2n plus 3n. Okay. So let's do another example. So prove by induction that 4 to the power of n is always greater than 2 to the power of n plus 3 to the power of n. For all n that is some natural number. That means we exclude 0. Okay? So start by doing the base case. Base case is left-hand side is going to give me 4 to the power 1, which is about 4. Right-hand side, we are going to get 2 to the power 1 plus... Wait, did I mess up the question? Hang on. 2, 4 to the power of n greater than... Oh, wait, n is greater than or equals to 2. Okay. N is a natural number, and n is greater than or equals to 2. So our base case should actually start with 2. So 4 to the power of 2 is 16. And then this one is going to be 2 to the power of 2 plus 3 to the power of 2, which is 4 plus 9, which is 13. So yes, 16 is greater than 13, so therefore the base case is true. All right, so what about the HK case? Well, where are you going to get n is equals to k? We're going to say that 4k is greater than 2k plus 3 to the power of k. Assume this is true. All right, and then for hk plus 1, when n is equals to k plus 1, we need to show that 4k plus 1 is greater than 2k plus 1 plus 3k plus 1. So this is our little objective here. And the way we go about doing that is by starting with what we know to be true, or what we, assume to be true. We're going to start with this guy. 4k greater than 2k plus 3k. And we're going to multiply both sides by 4. Which gives us 4k plus 1 here on the left, and on the right we get 2k plus 2 plus 4 times 3k. All right, and you can see from our objective here, our objective can also be written as 2k plus 1 plus 3 times 3k, right? Now, if you compare the right side of our objective with the right side of what we know to be true, you can see that what we know to be true is going to be greater than the objective. Okay, you can see this is 1, this is 2. So you can tell just by comparing the two here, term by term, that 1 must always be greater than 2. Right? Because this has a higher power, and this you're multiplying by 4 instead of by 3. So this guy is always going to be greater than this guy, which means if 4k plus 1 is bigger than this guy, 4k plus 1 must also be bigger than something that is smaller than this guy. Okay, so 4k plus 1 must be bigger than 2k plus 1 plus 3k plus 1. So there we go, we're done. So therefore, for n, so by induction, 4n is greater than 2n plus 3n. For all n is greater than or equals to 2. There we go. We're done. Okay, so that's it. We are done with series and induction. I suppose you could say the first chapter of further math. How many chapters of further math do we have in total? We have, let's see. Hang on, let me just go on here. For paper 1, you actually have 2 papers. For paper 1, you have 6 chapters in total. So that's our first chapter. Well, technically the first chapter, usually I would start with matrices, but I started with series and induction because I think it's a bit more interesting for the bridging. And matrices is also quite long, so I don't think we can finish that in the time that we have for the bridging program. So anyway, yeah, we are done with 1 chapter of further math. So you can actually try doing the passive questions that I've given you to see whether you, just to get an idea of what the difficulty is like. And the answers are, again, like I said, they are provided. So let me just show you the passive questions. I've actually shared this to you in the first class of the bridging program. Oops, hang on, let me just move that away. Right, so it's all here. So once you're done, you can just click that. That brings you to the answer, and you can click that to go back to the question. Okay, So you can give that a go, see whether you can actually do these questions. There are some questions that involve differentiation as well. So like something like this here. Let me just zoom in so you can actually see. There, proof by induction for all n greater than or equals to 1. When you differentiate this, you will get something like that, where this is a polynomial of degree n. So this is just differentiation, which I believe you've done it at math, so shouldn't be a problem. So yeah, that's it. So, do you guys have anything you want to ask so far about further math in general, or maybe this chapter, or any of the previous questions that we have discussed? Anything at all, or maybe the A-level program in general? Is there anything you guys want to ask? Because this is our last session. Okay. How about this? Since you guys have nothing to ask, and we still have a bit of time left, I will show you an interesting problem. Yeah? Okay, let's go down here. Let's say we have 10 to the power of 11. Oh, you know what? Let's make this a bit more ambitious. 100 to the power of 101 versus 101 to the power of 100. Now, the question I would like to pose to you is, which one is bigger? Which is bigger? So you can't use a calculator because you're just going to get a math error. So what do you think? 100 to the power of 101 or 101 to the power of 100? Which is bigger? Okay, let me do a poll. I think I can. Oh, what? Hang on. I just zoom out a bit. How do I do a poll again? It's like slash poll. Oh wait, hang on. Okay, so I'll let you think about this for a bit. And I'm gonna try to set up a poll here. Manage poll. New poll. Which is bigger? 100 to the power of 101 or 101 to the power of 100? Yeah, so I've created a poll. You can click that little thing on the above the chat. You can click that and vote. No idea. What does your intuition tell you? Let's say 3 to the power of 2 versus 2 to the power of 3. Which one is bigger? Four to the power of 3 versus 3 to the power of 4. What about 2 to the power of 3 versus 3 to the power of 2? What do you think? Okay, let's look at our results. 100 to the power of 101. That's a pretty good guess. You're actually correct. 100 to the power of 101 is actually bigger. Now, why is it bigger? Okay, I'm going to show you. Well, let's say we replace the numbers here with unknowns, right? So let's say we have y to the power of x versus x to the power of y. Now, I'm going to tell you that y to the power of x is in fact bigger than x to the power of y, provided that, you know, these things are greater than the value e, which is a bit of a weird assumption to make, but just bear with me for now. So I'm just going to get rid of this part here. Okay, so what we can do is we can, let's see, what was I trying to do again? Let me think. We can raise both sides to the power of xy. To the power of 1 over xy. Okay. Why am I doing that, you might ask? Well, we are going to get y to the power of 1 over y here. And this guy's going to give me x to the power of x over 1 over x. Okay. So if we are trying to prove this statement, it's the same as trying to prove this statement. Again, we haven't actually proven it. I'm just stating a statement here. Statement that has yet to be proven. Okay, so we're actually looking at the function y equals to x to the power of 1 of x. So we're trying to look at how this function behaves. So what happens if you were to graph out this function? Well, before we can go about doing that, we need to work out what the minimum point is, or the maximum point. So this one actually involves something called implicit differentiation, which is something that you haven't done yet, and I haven't actually shown you how to do. So I can't really show you this without going into implicit differentiation, but what I can show you is the graph of this function. So let's see. So suppose we plot y equals to x to the power of 1 over x. You would actually get something like this. As you can see, there is a maximum point somewhere here. And it turns out the maximum point is 2.718. As you know, that is the value of Euler's number, which is e. That's the constant e. So as long as your value of x is greater than the value of e, it's going to have this form right here. So let me just draw that. Hang on, let me just take a little picture here. Okay, I'm going to copy that. Let me copy this again. Copy that. Paste it here. There we go. So we know that the function looks like this, right? And let's say we're going to compare, let's say, 10 to the power of 11 versus 11 to the power of 10. So 10 to the power of 11 is going to be somewhere here. Just ignore these values here. We know that this is going to stretch out to infinity. So maybe 10 is here, and then maybe 11 is here, right? So this is when x is equals to 10. This is when x is equals to 11. So when x is equals to 10, we're going to get some value here. When x is equals to 11, we're going to get some value that is lower. Therefore, 11 to the power of 10 is actually smaller than 10 to the power of 11, as long as your value of x, which is this value here, is greater than e. So as long as x is greater than e, x to the power of 100 to the power of 101 is going to be greater than 101 to the power of 100. There you go. Yeah. So why can you not differentiate this? So let me just show you. And how do you even go about differentiating something like this? Okay. Because you can see here, the only thing that we know how to differentiate, or the thing that you have seen how to differentiate in AddMath, is if you have x to the power of n, you would get nx n to the power of n minus 1, right? This is what you know how to differentiate. But this guy doesn't look like this at all. So usually what you have to do here is you have to ln both sides. And remember, when you ln something, you can bring the power down like that, okay? And now you differentiate. So when you differentiate, you want to differentiate both sides like this. Hey, Elise, good morning. Hello, hello. Okay, so you differentiate both sides like that. So on the right side here, you're actually doing the product rule because you are differentiating two functions. They are products of each other. But then on the left-hand side, you might be wondering, what the hell is this? How can I differentiate something that's not a function of x? Because this is a function of y, right? you can only differentiate something with the same unknown as what you're differentiating with respect to. So what you can do here is you can use something called the chain rule to sort of cheat the system a little. So I'm going to multiply this by 1. So I'm not changing anything, right? I'm multiplying by 1. But instead of writing 1, I'm going to write dy over dy. So nothing has changed because dy over dy is still 1, right? And then we're going to differentiate this right side here with respect to x using the product rule. So 1 over x, and this guy gives me 1 over x plus ln x, and then that's going to give me negative 1 over x squared. Okay. So what I can do here is I can swap the numerators. So instead of this, I'm going to write this as d here and then dy here. I'm swapping the numerators around. Why can I swap the numerators, you might ask? Because when it comes to multiplication, multiplication is commutative, meaning a times b is the same as b times a. There's no difference. Therefore, we can do it like this. Is multiplication always commutative? No. When it comes to matrices, multiplication of matrices is not commutative. But we haven't done matrices yet, so we're not going to talk about that. Okay, but the point is, for normal multiplication, you can swap the order, right? So swapping the order, we can have dy dx times d dy times ln y. This guy's going to give me 1 over x squared minus 1 over x squared ln x. So if you look at this carefully, you'll see that, wait a minute, we can actually differentiate now. Oh-ho! So what happens when you differentiate ln y? You get 1 over y, right? So dy dx times 1 over y equals to 1 over x squared. I'm going to factorize this out, so I get 1 minus ln x. And then we're just going to move this down a little. So dy dx is going to be equals to y over x squared, 1 minus ln x. And there we go. So that's how you find the first derivative. And how do I find the stationary point? Do you guys remember how to find a stationary point of a function? You've done this in AddMath many, many times. I'm sure you know the answer to that. How do I find the stationary point of a function given the gradient function? What should we do? No one knows? What? Nani? You have to equate it to 0, right? You have to equate the dy dx to 0. Because at the stationary points, the gradient is 0. So 0 equals to y over x squared, 1 minus ln x, like so. And okay, you're gonna bring out the x squared so that this appears. Yes, that's right, Salpin, that's correct. So let's see. We have either y over x squared equals to 0, or 1 minus ln x equals to 0. Okay, so we're going to ignore this one because we're going to say that x and y are both greater than the value e. So we can ignore this guy here, which means 1 minus ln x equals to 0. So ln x must be equals to 1. So how do you get ln x equals to 1? X must be e, right? So therefore, my stationary point has to be when x is e. So when x is e, what is y? When x is e, y is 1, x to the power 1 over x. So it's e to the power of 1 over e. Okay, so our stationary point is at e1, hang on, e and then e1 over e. How do I know it is a maximum or minimum point? Well, you can do a second derivative, but if you do a second derivative, it's going to be very complicated here. So another faster way of doing the second derivative is by checking the gradient next to the stationary point. Because if it is a maximum point, then it's going to look something like this, right? And let's say this is your maximum point. So if you check a value of y on the left and the value of y on the right of the this guy here, you'll see that the gradients would be something like this. So the gradient here would be more than 0. The gradient here would be less than 0. So let's see, if we put something smaller than e, let's say we put x is 1. So if x is 1, what is my dy dx going to be? Well, if x is 1, then my y is going to be 1 to the power 1 over 1, which is just 1. So we have 1 times 1 minus ln 1. Ln 1 is 0. So we get 1, which is more than 0. Cool. What about when x is, greater than e? So let's say x is 2. So that means y must be 2 to the power of 1 over 2. So square root of 2. Okay, so dy dx is going to be square root of 2 over 2 squared, which is 4. And then 1 minus ln x is 2, ln 2. So using your calculator, 1 minus ln 2 is going to be 0.3. Wait, did I mess up something? 1 minus ln 2, x is 2. Oh, wait, sorry. 2 is not greater than e, my bad. So I should put x as 3. So x is 3, that means y would be 3 to the power of 1 over 3. So we're going to get cube root of 3 over 3 squared, which is 9. 1 minus ln 3. Okay, so 1 minus ln 3 is a negative number, which means we're going to get some dy dx that is less than 0. So therefore, we can conclude that this stationary point is in fact a maximum point. And then when you try to plot the graph, you would get something like this. There you go. Okay, so this is implicit differentiation, which is something that you will learn in A2 math, the second part of math. There we go. So that's it. So as long as your x is greater than e, you always choose this guy. Okay, so that concludes the bridging program for further math. I hope you guys found that interesting. Maybe you learned a thing or two. hopefully. And yeah, if you do choose to stay on in Kingsley, you would start your program in September 2021, and you would take your first exam in May, June 2022. So that would be your AS exam. So you have a couple of months, sit for your first exams, and then in May, June 2023, you would sit for your final exams, and then you would graduate then. So you have roughly 1.5 years. Yeah, roughly 1.5 years. Yep. There we go. That's it. All right. Goodbye, everyone. Bye-bye. Hope you guys had fun. And hopefully this gave you a good idea of what further math is about, and whether you think you would enjoy the subject. But yeah, for now, goodbye.